Yeah. Yeah, I'm tired anyway.
The grandkids, the
Yeah.
Why especially him?
Oh. Yeah. So who's it?
You know that one? No, I just forgot about it. Thank you. What's there after the GS475?
Yeah.
I didn't think maybe that's it. It's not on the website, right?
Yeah. But it's like, is there a type this into this? Morning. I understand that. Get their exam back. Somebody. No, yeah.
Probably looking at the old,
Probably not.
I am listening to it.
Like, yeah.
No, yeah. Yeah.
Like,
Oh, no, there's some of the EE section of material.
yeah, I don't know like how we at night. You didn't take it.
It'll be your plan. Yeah, so you got it. I missed all of the next one. So I didn't know you could.
No, I haven't fixed it. You want to have. I did like it.
Yeah, I heard you came to see George.
I got 3 out of 8. It can't be. What's the rest of the world like?
All right, so I handed back the exam. I'm not gonna go over that if, I think most people did better on this exam than the last exam, actually. If you have any questions about it, stop by my office and see me, and I'd be happy to go over any of the problems with you. I think probably the 2 problems that gave the most trouble were the transistor driver problem, and then actually the pull-up, external pull-up problem, and then and with regard to the programming, it was, I think it was maybe the 3rd or 4th problem, the one that dealt with the structs and writing the code for the structures. But if you have questions about that, come and see me. I want to finish up chapter 7 today. There's 2 topics left. There's string to number conversion, number to string conversion, and then also how floating point numbers are represented inside a microprocessor or computer. Have you looked at that in like 254 or anything? Floating point representation of numbers? Do you recall that? Recall looking at that? Okay. And then the next chapter, chapter 8, deals with a lot of interfacing. So, you know, how to hook something up via serial port, how to actually hook up the motor, how to hook up the display. So there's a lot of interfacing with that. So there are a lot of occasions where we need to convert a number, you know, either a floating point number or an integer, to a string. We have to do that when we actually send it out to the display. Fortunately, printf will do that for us. We also need to occasionally convert from the string format, an ASCII coded string, into the corresponding number. Then we've got some routines. Scanf is the one we typically use when reading from the terminal. But if we've got them already stored in strings and need to do the conversion, to convert string to number, there are some handy C library routines. There's A to I for ASCII to integer, and then string to long, which I think A to I is just a macro wrapper around string to long, but these actually will take a string argument, and then I'll show you some examples in just a second, and then return a corresponding integer or float. There's A to F, and then string to F. You can also use scanf instead of scanf or fscanf. Scanf will read from the terminal. Fscanf will read from a file. Scanf will actually read from a string and do the conversion for you. It can also be used. So just some example code here illustrating how to use a couple of these routines. Now this is a string, it is not a number. It consists of 4 ASCII bytes and a trailing 0 byte, but we can't, you know, use it as a number to do arithmetic. We need to convert it to a binary int form, or sometimes we're dealing with floating point numbers, 3.7 e to the minus 4, for example. And that's a string, it is not a floating point number, but and A to I is really easy to use. A to I, and then just pass it the string. And this would then do the conversion. Of course, n is going to be a binary number internally, but it's the binary number that corresponds to the decimal number 1, 2, 3, 4. And then similarly, A to F works similarly and would set F equal to 3.7 times 10 to the minus 4th. Scanf, normally scanf will automatically read from the input terminal or the keyboard. Scanf, the first argument has to be a file pointer. Scanf, the first argument is a string, and then comes the conversion specifier. Like this would be for reading an integer from a string. And then with all the scanf routines, then we have to pass a pointer that's used as a return argument, or an output argument. And so that would actually set I equal to whatever number is contained in the string. We're using a fairly full-featured microcontroller that has a lot of libraries, has a lot of memory. These are becoming relatively inexpensive, so you guys are lucky in some sense that you can buy these microcontrollers for just a few dollars to use in projects. But it wasn't that long ago that we were really limited in our choice of microcontrollers that didn't have a lot of memory, and so often you would try to avoid using linking in library routines. And in particular, printf and scanf would take up a lot of program memory. They're actually fairly huge library routines. So you would often, especially for integers, it does take a lot of work actually to convert floating point numbers from their string representation to their internal binary representation. But if you're working on a project that just is using integers or is using scaled fixed point, we talked about last time, you can do the conversion to integer without a library routine. And perhaps save yourself some program memory. It's not something that we maybe worry about too much these days, but you might find yourself in a situation where the amount of available memory is restricted. This is actually relatively pretty easy to do. You can do it with just a simple loop for I equals 0, I less than the length of the string. And then we'll do n is 10 times the previous value of n. So what we're going to do is actually just read in the digits from the string one at a time. We'll initially set n equal to 1. Then we'll go around, read in the 2, multiply the previous value of n by 10, and then add 2 to it. Then come around, multiply the previous value of n by 10, so it becomes 120, add the 3. Multiply that by 10, so it becomes 1,230, and then add the 4. So it's 10 times n plus string. Now we can't add in just string of I because that's the ASCII code. But the ASCII codes are consecutive. The ASCII codes for 0 through 9 are consecutive integers. So if we subtract off the ASCII code for 0, so let's say this is the ASCII code for 1, if we subtract, now this is not a 0, this is the ASCII code for 0, then we would be left with 1. Sometimes that's written as in the hexadecimal notation. ASCII 0 is a hex code 0x30. That'd be 48, I guess. So the reason this works is the ASCII codes for 0 to 9 are consecutive. And they're in hexadecimal, they're 30 to 39. So if we subtract, if we read in an ASCII code of 39, which would represent the number 9, subtract hex 30 from it, we're left with the value 9, the integer value 9. So it looks a little odd, but here, this is just another representation for hex 30, and so subtracting that from the ASCII code gives us the actual number. there are times where we want to convert our numbers to strings, especially when we want to, display them, send them out to a terminal. And we've got printf for doing the conversion. Okay, so and sending it to the terminal. Again, it does, when you pass printf a number, it's not just sending that integer number to the terminal. It's doing this conversion to actually an ASCII string, 1, 2, 3, 4, internally has some binary representation as this number. Printf is actually converting that to the ASCII string 1, 2, 3, 4. So it actually be hex 31, hex 32, hex 33, hex 34. Those bytes then are actually sent to the terminal. You can use sprintf. To actually convert a number to its corresponding ASCII string representation. Of course, here I'm just passing a number. Typically, this would be a variable like n or x or something like that. And certainly, if you're having to do conversions of floating point numbers, this is often the easiest way to do that, to convert a floating point number to a string. There isn't, unfortunately, an F to A library routine that's available. Some C libraries actually do provide an I to A, but it's not part of the standard C library. But sprintf for doing the conversion is typically always available. You do have to be careful with this. You have to make sure that the string is large enough to hold the number, right? Otherwise, you get what's called a buffer overflow. You can also do the integer to string conversion without sprintf. I'm not going to go through the details of doing that, but actually just divide the number by, find the remainder with 10, and then add the hex, the ASCII hex offset. We convert it to the corresponding ASCII code. So do that in a loop. Actually, that produces the string in reverse order, and then reverse the string. It's one way to do the conversion. Or you can do it recursively. There's a neat recursive way to do it. The problem with printf in particular is it can be huge. I mean, the library routine implementation of printf can be huge. So that can really increase the size of your program when you have to link in printf. So various compilers provide kind of workarounds for pulling in the full printf with compiler options can be used to select smaller limited versions. And this is very compiler specific, but for the TI compiler that we're using, if you add the compiler option --printf _support, and then by default, it's full. That means give me the full-blown version implementation of printf, which can be large. And then they've got another option that says, give me a version of printf that will allow me to print integers, but not floating point numbers. And it's much smaller. And so that can make your program size much smaller. So if you are in your program, you're never using floating point numbers, this is probably something you'd want to do. It would dramatically reduce the size of your program. And then there's actually a third option that's minimal, that even only does limited integer support. Again, this is for the TI compiler. On the GNU compiler, they actually have different versions of printf. There's an iprintf that but then you have to rewrite your code. Okay, so everywhere you use printf, use iprintf, which only works with integers. But again, that's usually pretty easy to do, and can drastically reduce the size of your code. All right. So let's talk about how floating point numbers are represented inside a computer. Integers are fairly straightforward at this point, hopefully. 2's complement representation, almost always to represent integers inside a computer. There have been various ways to do this. The IEEE had developed a standard representation for floating point numbers for both floats and doubles. So a float is 32 bits or 4 bytes, and a double is 64 bits or 8 bytes. So, and this has become almost standard for almost all modern computer systems. Use this IEEE standard representation for floating point numbers. So we'll look first at a float. I'll only mention a double briefly, but if you understand how a float is represented, you'll understand a double. They use a form of scientific notation, but it's actually a binary number. Okay, so it's, in binary, it's 1.01100 times 2 to the whatever power would be the binary representation. But in 32 bits, you've got 1 bit that's used for the sign to indicate whether the number is positive or negative. And then you've got 8 bits E7 through E0 that make up the exponent of the number. And then that leaves actually 23 bits that make up what are called the mantissa of the number. So S here is a sign bit, and the 0 is positive and 1 is negative, okay, for the number. And then E, the exponent, it's an 8-bit, what's called a biased exponent. I'll talk more about that. But it's in the range between 0 and 255. It's 8 bits, so 256 different values. And the mantissa is a 24-bit binary fraction. And it's 1.M1, M2 through M23. So this mantissa always has a value as a binary fraction between 1 and 2. Now, if you think about standard scientific notation, which you were taught, I don't know, in elementary school or high school or something, it's always a leading digit, right? 1 point something, 3 point something times 10 to the 24th, 3.5 times 10 to the 24th, or 7.639 times 10 to the minus 12th. Okay. So in standard scientific notation, you always have a leading digit, a decimal point, and then some power. Well, the binary representation or binary scientific notation is always 1 point something, okay, and then times sub power, and the 1 point something makes up the mantissa. Since this number is always 1, we don't actually have to store the 1. It's assumed. Okay, so we always have to scale our number. So it's some fraction times 2 to the exponent. Okay, I'll talk a little bit more about this. But since in binary, in our binary scientific notation, that leading number is always 1, you'll see we can scale the number so that that's true. Since we know that's always 1, we don't have to store it. So it's actually not stored as part of, it's a wasted bit. Okay, so it's just assumed. Okay. So the floating point number is, the floating point value can be calculated. It's -1 times s, 2 to the, this is where the bias exponent comes in, 2 to the power e minus 127 times m. You know, standard scientific notation, I guess you'd write this, and maybe I will. M times 2 to the e minus 127. Okay. That's how you calculate the corresponding floating point value, you know, as a decimal value from this representation. S is either 0 or 1, so -1 to the 0 is 1, -1 to the 1 is -1, so that takes care of the sign. And then it's always, this mantissa is always 1 point something, a binary fraction, times 2 to the exponent minus 127. Okay, that's what this biased representation is. Instead of doing that, they could have used 1 for a sign bit, but with this biased representation, if E is less than 127, this is going to be negative, right? So if E is 126, that actually represents 2 to the -1. If E is 127, it represents 2 to the 0th power. If it's 137, it'd be 2 to the 10th power. So the values here for E, it's an 8-bit number, so it can range from 0 to 255. But the values of E that are less than 127 represent 2 to the -1 is half, right? 2 to the -2 is a quarter. Okay, so it would represent numbers less than 1. Is that clear? Kind of? Okay. We'll look at some examples on how to calculate it. Okay. But there is, so really, you know, with a 32-bit number, there really only are, what, 4 billion and something possible floating point numbers that we can represent. That's all we can represent in a 32-bit number, 4 billion and something different quantities. In this case, we're using 24 bits to represent the mantissa, and then the exponent here can vary. So typically, E is actually between 1 and 254, and I'll talk about why in just a second. So the smallest value you can represent is plus or minus, depending on the sign, with E equal to 1, and the smallest mantissa would be 1. Okay. Mantissa is always between 1 and 2. 2 to the -126. That's approximately 10 to the -38. You can verify that on your calculator. It's actually like 3 times 10 to the -38 or something, but as an order of magnitude, that's the smallest number we can represent as a float, approximately 1 times 10 to the -38. The max largest value we can represent. Now, the largest value of the mantissa is actually 1.111111, or very close to 2. And then the largest exponent is 254. So minus 127, that gives us 127. And that's about 10 to the plus 38 is the largest floating point value that we can represent using a float. Doubles allow us to represent a lot larger numbers. Okay, so what about the value of E of 0 or 255? Actually, there are some special numbers that you can represent as floating point. You can actually have plus or minus infinity. You can also have what are called nada numbers. So like division by 0 in a floating point will actually give you not a number. And then there's an exact representation of 0. So those are the special cases. When E, let's see, I've got it written down here. The value of E is, when E is 0, it's used to represent 0 if all the mantissa bits are 0, or what's called a denormalized number if they're not 0. If E is 255 and all the M bits are 0, then the number represents either plus or minus infinity depending on the sign bit. And then there's some special rules for working with plus or minus infinity. Plus infinity times any number gives you plus infinity. Okay, plus infinity. But it just represents the largest possible floating point number that you can get. And then if the mi are not all 0 and the exponent is 255, it represents not a number. A double uses an 11-bit exponent with a bias of 1023 and 52 bits for the mantissa fraction, the fractional part of the mantissa. Otherwise, it's fairly similar, just a much larger mantissa and a larger exponent. So you could stick into the corresponding formula here and find out what the corresponding minimum and maximum values you could have for a double. So to convert a number x to its binary representation, I'll give you a little recipe or algorithm. S is 1 if x is less than 0. Otherwise, s is equal to 0. That's easy, right? So just an if x is less than 0, the s part of the representation is 1. To calculate the exponent that's needed, you're really trying to find, the solution to, this problem where m is between 1 and 2, and then solve for this exponent. So it's actually, you can use logs to do that. It's the log of the absolute value, because now we've got the s is taking care of the sign, divided by the log of 2. Okay, doesn't matter whether you use natural log or log base 10. This is actually the e minus 127 to calculate the actual exponent. you take that value and then add 127 to it. That's the offset that you need. And then the mantissa is then the absolute value divided by 2 to the p power. And then we can get the value of the bits by subtract. Remember, this will give us a number between 1 and 2. It'll be 1 point something always if we've done this right. The floor function, if you haven't seen that before, that always rounds down toward negative infinity. So like 3.7, the floor of 3.7 is 3. Okay, you know, we're rounding 3.7, we give you 4. But the floor of 3.7 is 3. The floor of negative 3.1 is negative 4. It always rounds toward negative infinity. There's also a ceiling function or ceil function that always rounds toward positive infinity. This part is round n minus 1 / 2 to the minus 23rd. Okay. Because there's 23 bits in it, so this just will subtract the 1 from the number, and then dividing by the 2 to the 23 will actually just shift the whole thing over and gives us the corresponding value for the 23 bits of M. Then we can form the 32-bit pattern. We just shift the sign bit 31 positions to the left, add the exponent, shift it 23 bits, and then add in our mantissa. This, I'm using strange notation here. This is just a number. Okay, M1, it's M1 through M23. That is just a value that's equal to this. Okay, so this is just that same value representing those 23 bits. So if you want to pull out your calculator, we'll find the binary representation of 12.5. So you don't need your calculator for this. What should the sign bit be? It should be 0, right? It's positive. And then P would be floor log of 12.5 divided by log of 2. So actually, compute this part first. Log of 12.5 divided by log of 2. Does anyone have a calculator on my right? You guys use the log base 10. You guys use natural log. Should get the exact same ratio as a property of logarithms. But just compute log of 12.5 divided by log of 2. It really is asking, you know, how many bits does it take to represent 12.5? Well, we can represent 8 with 3 bits, 16 with 4 bits, so it's really between 3 and 4. But we always round down, that's what the floor does. So this ratio should be 3 point something, right? Is that what you're getting? So if it were, you know, 8, it would be exactly 3. But so this is really just saying how many bits does it take to represent that as an integer thing, is what this is doing. So it's 3 point something because of the floor. It doesn't matter if this were 3.99. P would be equal to, in this particular case, 3. So the exponent value is 130. Now, of course, this is the decimal value. That's actually converted to the 8-bit binary value when it's stored in as part of the floating point number. Now, the full mantissa would be calculated using this 12.5 divided by 2 to the third. Now, if we've done the previous step right, this should always give us a value that's between 1 and 2. Okay, so what do you get on your calculator? It's 1.5625. Okay. And then the last step is M1 to M23 is we're going to actually multiply this by 2 to the 23rd, or equivalently divide by 2 to the minus 23rd, however you want to do it. And what do you get? It's going to be a long number. Okay. Yeah, I got 47,18592. Okay. And you need to carry this all the way out to, point whatever, because this is the integer value that's going to get stored in those 23 bits. Okay. If it turned out to be like 0.6, we'd round this up to 3. Okay. Because this is the best. When we convert numbers to the floating point representation, it's an approximation. We don't always have an exact representation for our numbers as floating point. We do this rounding here, so it's going to be hopefully a close approximation, but it's never an exact approximation. There are some even standard decimals. This may turn out to be an exact representation here unless there was a decimal point. But I think like even 0.1 or something like that may not have an exact representation as a floating point number. So then we form the whole bit pattern. We don't have to worry about S, it's 0, but we can form the number by multiplying E by 2 to the 23rd, that's shifting it left, and then just adding in this number. And when I did that, I got 1,009,523,7,632. Now this is the integer representation of that 32-bit quantity. It's interpreted by the computer as a floating point number. Now, fortunately, on your calculator, you can convert that to hexadecimal. So it's stored, here's the 32-bit quantity. So the actual binary pattern of 12.5, if you looked at it, if you looked at the bits, it would be 4, and then 1, and then 4, and then 8, and then 4 zeros, 4 zeros, 4 zeros, 4 zeros. That's the 32-bit pattern that would be used internally to represent that 32-bit number. And I can show you that. I'll put these I don't have a compiler on this computer yet. What? You don't want to do that very often, right? So it's easy to write a computer program to do that conversion for you. And I know you can't really, it's tough to see the font size there, but we converted 12.5. And so it should give us, it says a p-value of 3, an exponent of 130, and then the mantissa fractional portion is 4718592. And then, so this is the corresponding hexadecimal. And then that's interpreting that as a floating point. A little more interesting is another program, and this is really simple. I'll show you the code, where you enter the integer value. And it'll give you the corresponding decimal representation, which is 12.5. But all this really does, and I know you can't see this, it reads it in as the 32-bit integer. And then, but I have to trick the compiler into thinking it's a float. I print out all the parts, but so what you do is that you take the address of the integer, cast it to a floating point pointer, and then dereference it. So it's interpreting the same 32 bits as a floating point number and printing it out as a floating point number, and you get the 12.5. So it's a simple little program to interpret these binary patterns as the corresponding 32-bit numbers. Now you can imagine, wasn't that long ago, that we actually had PCs that didn't have hardware support for these floating point numbers. So to add floating point numbers, you would have to shift them so that they have the same exponent, so you can do the addition, just like you have to shift numbers when you're adding them in scientific notation. Multiplication is a little bit easier, right? You add the exponents, multiply the mantissa, and then store it back. So you could write libraries of routines that directly manipulated these 32-bit patterns without using what's called a hardware floating point processor. Fortunately, almost all modern computers have floating point processors. Now, the original IBM PC didn't have a floating point processor. It wasn't until the 486 processor came out that was a standard part of every PC. There were even the 386 processor did not have a floating point processor. There was a 386 DX, if I recall, that did have, and then there was a 386 SX that didn't have. It's called the 386 SUX or the SX because it didn't have a floating point processor. It could still do floating point arithmetic, but it had to do it using a software library, right? So it was much slower for floating point calculations than the 386 DX. Now it's only been very recently that we found floating point processors in microcontrollers. Like the one we have actually has a floating point processor in it, and it can do floats and doubles. I'll just mention that briefly, but that's rare. Okay, still fairly rare. You'll find a lot of microcontrollers for embedded systems that do not have floating point processors. So if you have to do a lot of floating point, and it's true with a lot of high-speed processors, like even graphical processors. Floating point arithmetic in general can be slow and time-consuming. So, but maybe you can avoid it by doing fixed point arithmetic, like we talked about last time. Or again, if you're lucky, you might have a floating point processor available. And ours does. So I just wanted to make a note about it. It has what's usually called a floating point unit or an FPU to contrast it with the CPU, the central processing unit. It has 128 bytes that can be arranged as 32 4-byte float registers. They're called S0 through S31, or 16 8-byte double registers. D0 through D15. And these have, to access this, there's a completely different set of assembly language instructions that are similar to the ones that we've been using. This is one to actually load a floating point register from memory. So remember, that's a memory address. So that would be from the address that's stored in R0. Take that 32-bit floating point value, so those 4 bytes in the memory pointed to by this register, and actually store that in this floating point register. We have to move move numbers into the floating point register from memory, and then back into memory after we're done processing them. This is not a program. I'm just showing you some typical instructions. So guess what this one does? It adds the 2 floating point numbers that are in S1 and S2 and stores the result in S0. And then you've got, in addition, multiplication instructions. S0 be S1 times S2. And you've got all the trigonometric instructions. So I'm not going to have you write assembly language programs using the floating point processor. But if you actually looked at, last time we went through that procedure on looking at the generated assembly, if you wrote some C programs that did some work with floating point numbers or double numbers and looked at the generated assembly, you would see in the assembly language file instructions like these. And these are instructions to actually load numbers into the floating point processor. All right, that's wraps up. I am going to give you some homework related actually to the number conversion, and then also on writing assembly, but you don't have to actually write assembly. You write the C code. Actually, I'll give you the C code, but you have to convert that to assembly and then link it in. Let's see. I gave back the exams. Did anyone? Heard anything about Easton? Was he here Friday? He was here Friday, but he wasn't here. He was in class this morning either. Was he here on Friday? I think so. All right, that's it. Get out of here. See you in a couple hours.